remote videos. So today we are going to be looking at torque. Okay. So this is unique in that torque is a force. So just like we've been talking about this unit, but it's going to be a force that attempts to rotate an object. Okay. We're going to represent torque with this little cow right there. And when we talk about torque again, that is a force that attempts to turn an object. So since it is a force, it is going to be a vector. So we need to include magnitude and direction. Since we're looking at rotation, we are going to look at whether our torque would want to make our object rotate clockwise or counterclockwise. Okay. So if torque is attempting to rotate our object counterclockwise, we're going to say that is counterclockwise torques are positive, whereas forces or torques that attempt to rotate clockwise, we're going to say that these are negative. So we'll need to look and see which direction that torque or that force would make our object want to rotate. Okay? Also, since we are looking at forces, our unit for torque is going to be a Newton meter. Okay, so it's a little different than earlier. So unit for torque is going to be a Newton meter, and the maximum torque we are most likely to rotate our object is going to be when we are applying the force at a 90-degree angle. Okay, so we are pushing straight on, and when your lever arm is long. So what that means is that you're pushing far away from the hinges or from that turning point. So if you think about opening a door, you push at the end opposite where the hinges are, you push straight on. You push at a 90-degree angle because that's when we have the maximum torque. Okay, we have the largest perpendicular component. So all that torque is going just into rotating our object. Okay. Okay. On the flip side, when we have the smallest torque, or when torque is equal to 0, this is going to be when we're pushing parallel to our turning point. So this would be when theta is equal to 0 degrees or 180. And we're going to make that perpendicular component the torque that's actually pushing to rotate the smallest possible. In this unit, we are all at equilibrium. Okay, so we're either moving with a constant velocity or we are motionless. Okay, so this is going to be when the sum of all of our torques are equal to 0, or all of our clockwise torques equal our counterclockwise. Okay, so they're basically canceling one another out. And torque is nice because when we are balanced, our clockwise and our counterclockwise torques are equal to one another. We are actually not turning. So when looking at torque, we know when we're in equilibrium, our torques are balanced. Our object is not going to be turning. Okay? We are going to be calling that turning point the fulcrum. Okay, so when you see that word fulcrum, that's just the point that our object is going to rotate about. Okay, let's go ahead and look at some examples. Equation that will help us calculate what our torque is on an object, or what torque are we applying that is attempting to rotate an object. So our equation for torque is going to be our radius times the force that you're applying times the sine of the angle that you are applying that force at. Okay, because the sine is going to tell us what component of that force is being applied straight on. What is that perpendicular component of that force? Okay. And when we talk about radius, or the R, that's going to be the distance to the fulcrum, or to the turning point. Okay, so it's just however far away your force is from that turning point. Okay, so if we look at this example, we have a mechanic tightens lugs on a tire with 110 newton meters of torque at an angle of 47 degrees. What force must be applied if the wrench is 0.4 meters long? Okay, so looking at this, we're given a couple things. It tells us that our torque is 110 newton meters, okay, that we're applying that torque at a 47 degree angle, and our radius, or we're applying that force 0.4 meters from that pivot point or from that fulcrum, okay? And our goal here is to find our force. Okay, so we can plug these values that we know into our torque equation. So remember, we're going to have torque is equal to our distance to that fulcrum times force times theta, okay? So we would do 110 as our torque is equal to our radius of 0.4, because we are applying that force 0.4 meters away from that pivot. Sine 47. Because we are only concerned about that perpendicular component. How much of that force is actually being applied in the perpendicular direction in order to turn that wrench? Okay. So if we want to solve this, we'll need to divide each side by 0.4 and sine 47. And we would be left with that our mechanic needs to apply a force of 376.02 newtons. And how long a wrench has to be now if we can only apply 275 newtons of force? So we're still going to have 110 newtons of force, and we're still applying our force at a 47 degree angle. The only difference is now that we can only apply 275 newtons worth of force. So we need to see how long our wrench should be in order to get this wrench to rotate. Okay. So use our torque equation. Torque is equal to radius or force sine of our angle. So the component that's actually acting perpendicularly that would cause it to rotate. So torque is 110. We don't know our radius, but we do know our force now is 275. And sine of 47 tells us how much of that 275 is actually going to make it want to rotate. So to get our radius by itself, we need to divide both sides by 275 sine 47. And we should now see that our wrench would need to have a length of 0.547 meters. So we can see that as force goes down, if we want our object to rotate or have the same torque, then our radius needs to go up. Okay, so the longer the radius, the further the distance is from the turning point, the more force we're going to have, or more torque. And child standing on the edge of a seesaw, and we want to see where we would need a 70-kilogram kid to sit in order to balance that seesaw. So here we are balanced, which tells us all of our forces or all of our torques making our seesaw want to rotate clockwise has to equal all the torques that would want to make the seesaw rotate counterclockwise. Okay? So we first need to look and see what objects would want the seesaw to move or to rotate. So the first thing we have is this 50-kilogram kid on the far right. That 50-kilogram kid would want to make his end of the seesaw move down, which would cause that seesaw to rotate clockwise. Okay? So that kid on the right, that end of the seesaw would go down, which would cause it to rotate clockwise. Once we put our 70-kilogram kid on the other side, he's going to want to make the left side go down or make it rotate counterclockwise. Okay? So we have our two kids making our board want to rotate. We are not going to have anything else here because the fulcrum is at the center of that seesaw. Okay, so when the fulcrum is at the center, of our board, plank, whatever it is that's rotating, then we do not need to worry about the torque from the board itself. Okay, so when the fulcrum is at the center, we do not need to worry about the mass of that seesaw. Because if we just had the seesaw, if it's perfectly in the center, it would balance by itself. Okay, so we do not need to include any torque or any force of rotation from the seesaw itself, because when the fulcrum is at its center, our board will not want to rotate, okay? It's only when that board would want to rotate on its own that we would need to worry about the torque from that object. Okay. So let's look and see what values we know here. So if we look at our counterclockwise torque, okay? Remember, torque is equal to radius times force sine theta. Okay. So for our clockwise torque, that's from our 70 kilogram kid sitting on the other side. So, a 70 kilogram child is going to sit. So we do not know our radius. We're going to leave that as an unknown. Okay, when it comes to our force, okay, so we know we have a mass of 70 kilograms, but kilograms is not a force, okay? If we think about that child, the force that he's pushing down on the board with, that is going to be our force of gravity, okay? So the force that child is going to be equal to the force of gravity of that kid, okay? And we know our force of gravity equals the mass times 9.8. So to get the force of gravity that this child is exerting on our seesaw, we would take that mass of 70 kilograms times 9.8. Okay. Then we need to multiply by the sine of our angle. Okay. Since he's pushing straight down, that sine is going to be of 90 degrees. They're pushing straight down, so that angle is going to be 90 degrees. Okay. So that's from our counterclockwise torque. So I actually fluffed these a little bit, but that's okay because we'll get the same answer either way. We're taking our counterclockwise torque and setting it equal to our clockwise. Okay, so now we need to look at the torque from our 50 kilogram child. Okay, we know that he is sitting 5 meters from the fulcrum. So we know that the radius for the other child is 5 meters. The force that that child is pushing down on our seesaw with is also his force of gravity. But this child has a mass of 50. So to find his force of gravity, we would do 50 times 9.8. And then the sine of our angle. He too is pushing straight down, so it's going to be sine of 90 degrees. Sine of 90 is just 1. So if you want to ignore that component, that's totally okay, because we're just going to be multiplying by 1. Okay. So now the physics is done. We just need to do some algebra. So we divide each side by 70 and 9.8. And we should find that our 70 kilogram child needs to sit 3.57 meters from the fulcrum. Remember that radius always tells us the distance from the fulcrum. And if we want our seesaw to balance, he needs to be on the opposite side. Okay, we need someone trying to make it rotate counterclockwise. Okay. So we can see that when our force is greater, we don't need as long of a radius or as long as a lever arm in order to get a lot of torque. Okay, so as our force increases, we only need a shorter distance from that fulcrum in order to get the same amount of torque. Okay, so for this one, we would find that he needs to sit 3.57 meters from that center. Here, our turning point, our fulcrum, is not at the center of board. Okay, so since it's not at the center, that board, if it was all by itself, it would want to rotate. So here we need to take into account torque from the board itself. Okay. So if we look at this, we have a plank that's 10 kilograms. We want to see what mass our ball needs to be in order for that plank to balance. So we know for balancing, our counterclockwise torques have to equal our clockwise torque. So we need to look and see what direction each object would make the plank want to move. If we look at our 5-kilogram object, that would want to make that side move down. So it would end up making our board rotate clockwise. Okay, so when we look at our clockwise torques, we're going to have the torque, the force of rotation from that 5-kilogram ball. Okay. If we look at our mystery ball, however, that would want to make this side move down, which would make it rotate counterclockwise. Okay. So we're counterclockwise, we have the torque from our 1.2 kilogram, or sorry, our unknown ball. Okay. So those are the objects that are on the board, but we also said that the board itself would want to move if there's no objects on it. Since there is a larger mass on the right-hand side, that right-hand side would move down, which would cause the board to rotate clockwise. So since we have two torques that would want to make our board rotate clockwise, we're going to add those two together. Okay. Once we figure out what direction each object would want to make our board want to rotate, now we can use our torque equation. Okay. So if we look at an unknown that's making our board want to rotate counterclockwise, it's 1.2 meters from the fulcrum. Remember, your radius is always the distance to the fulcrum. Okay. We do not know the mass of that ball. Okay. And just like in our last problem, it's going to be the force of gravity from that ball that's pushing down on the plank and causing it to rotate. Okay, so our force here that we're looking at is going to be force of gravity. And again, we know force of gravity is equal to mass times 9.8. So since we don't know our mass of this object, we're going to leave that as our unknown. Okay. We would again multiply that by sine 90, since it's pointing straight down. But the sine of 90 is just 1, so I'm going to leave that out. Okay. So then that's equal to the sum of our clockwise torques. So for our clockwise, if we look at our 5-kilogram mass, remember, radius is always the distance to the fulcrum. Okay, so if we look at the 5 kilograms, it's 3 meters from the center, but then that center is another 2 meters from that turning point. So the total radius for that ball then is going to be 5 meters. Okay. All right, so again, it's the force of gravity from that ball that would cause our plank to rotate to your mass, which is 5 times 9.8 to get our force of gravity. Okay. We could do sine 90, but again, it's just 1, so we don't need to necessarily include that. Okay. But to that, I'm going to add the torque from the board itself. Okay, so the force of rotation that the board would have on its own. There, we want to find the distance from the center of the board to the fulcrum. Okay, so when we're looking for the torque from the board itself, our radius is the distance from the fulcrum to the center of the board. So if we look at this board, we can see that its center is going to be 2 meters from the turning point. Okay, so we're going to use 2 as a radius. And then it tells us that our plank has a mass of 10 kilograms. Again, it's the force of gravity from that plank that would cause it to move downward, cause it to rotate. So to find our force here, we're going to do our mass of 10 times 9.8. Again, we could do sine 90, but since that's just 1, we can leave that out. Okay. So from here, the physics is done, and it just becomes algebra. So add up your clockwise torques. And then we will divide by 1.2, divide by 9.8. And we should find that our mass here, 37.5 kilograms. Make sure when you guys are using your masses, you always use mass of kilograms. Okay, awesome. Okay, so here we have a 10 kilogram mass on the right hand side of our board, and then a rope attached to the end of our board in the ceiling. Our goal is to find the force of tension in that rope. Here, the fulcrum is at the center of the board, so you do not need to worry about the torque from the board itself. Okay, so go ahead and give this one a whirl. When you are done, go ahead and come back. So pause it, work on it yourself, and then come back to double check your answer. 8.8. So to do this, again, since we're balanced, we want our counterclockwise torques to equal our clockwise torques. If we look at our two objects that would cause this board to rotate, a 10 kilogram block would want to make its side move down and cause that board to rotate clockwise. The rope, on the other hand, if we just had that rope, it would pull its end up and make our board rotate counterclockwise. So we took the torque from the rope and set it equal to the torque from that block. Okay? And then we just use our torque equation. Remember, torque is equal to a radius times our force times theta, where radius is the distance to that fulcrum. Notice here how we did not multiply that force of tension by 9.8. Remember, we only do that when we're trying to find our force of gravity. Okay, so here, since the tension is not a force of gravity, we do not need to multiply by 9.8. Okay? We do, however, need to multiply the mass of the 10 kilogram block by 9.8 to find the force of gravity that it's pulling down or pushing down on. Okay, but once we set up that equation, it no longer becomes physics and it's an algebra problem. And we should have found that we had a force of tension of 94.84 newtons. All right, please let me know if you guys have any questions. Otherwise, I hope you have a great day.